1 pound is the maximum weight of a specialized fishing rod that must maintain structural integrity while under the tension of a sea creature weighing several hundred pounds. Why does such a lightweight tool not shatter under the extreme mechanical stress of a deep-sea hunt? It only looks obvious that the strength is a result of the angler's movements, but in reality, the durability is engineered through a complex internal architecture of composite layers. The process is only gaining momentum within the industrial facility. Engineers precisely calculate every single fiber angle to ensure the rod distributes energy across its entire length. One can notice how automated rollers apply thin sheets of carbon fiber onto a tapered steel mandrel with millimeter-level accuracy. Everything only gets more complicated when determining the specific resin-to-fiber ratio during the initial assembly. Each processing step is tightly controlled to dictate exactly how the finished product will bend and transfer kinetic force back to the handle. It is visible how the equipment gradually applies pressure to remove air pockets from between the microscopic layers of material. But this is just the beginning of the manufacturing cycle. The material responds to real-world conditions based on the orientation of the longitudinal and helical fibers wrapped around the core. This meticulous journey involves multiple thermal treatments and structural tests to verify the limits of the composite matrix. The transformation of raw synthetic fibers into a precision instrument requires constant monitoring of the curing temperature. At first glance, the rolling of these sheets seems like a repetitive mechanical task, but in reality, a single degree of deviation in the fiber alignment can lead to catastrophic failure during a heavy load. It does not end at this stage, as the rod must undergo finishing processes to seal the external surface against salt and moisture. One can notice how the tapered profile of the rod is shaped through several stages of grinding and coating. These technical layers are applied in a dust-free environment to prevent any microscopic contamination that could create a weak point in the structure. The equipment moves with a steady, rhythmic pace to ensure an even distribution of the protective polymer. The final structural check confirms that the rod can withstand the prescribed tension without losing its original shape or elasticity. From here, the finished component moves toward the assembly of guides and handles, having completed its primary structural evolution. Thus, the material reaches the standard ready for the further stage of final hardware installation. $1.8 billion is the approximate annual revenue generated by the global fishing rod market, serving a spectrum of users from weekend hobbyists to elite athletes in professional sport fishing competitions. Why does such a seemingly simple piece of equipment command such a massive industrial footprint? A single rod might appear lightweight and uncomplicated when held in the hand, but in reality, it is the result of a continuous and highly sophisticated industrial production system that spans the entire globe. This massive manufacturing network operates without pause to meet a staggering demand. Over 100 million fishing rods are manufactured and circulated throughout international markets every single year. One can notice the immense concentration of this demand in specific geographic regions, particularly across the United States, Europe, and Australia. But this is just the beginning of the complexity. The sheer volume of production necessitates a supply chain capable of handling millions of units while maintaining rigorous structural standards across every single piece of equipment. It only looks obvious that a rod should be made of traditional organic materials, but modern engineering has moved far beyond the past. Today, the vast majority of high-performance fishing rods are constructed from carbon fiber, a high-tech material that was originally developed for the rigorous demands of the aerospace industry. What surprises many people is that bamboo, once the primary standard for construction, has been almost entirely replaced by these synthetic composites. It gets more complex further on. The shift to carbon fiber was not merely for weight reduction, but for the specific mechanical properties the material offers under extreme tension. The equipment used in these factories must manipulate these fibers with extreme delicacy and consistency. It is visible how the camera glides along the assembly lines where layers of carbon are stacked. At first glance, the material itself seems to be the primary factor in a rod's quality, but in reality, the true performance is determined by the precise way each individual structural layer is arranged. Every fiber must be positioned according to a strict geometric pattern to ensure the final product can withstand the stresses of casting and hauling. The manufacturing process is governed by specifications that are accurate down to fractions of an inch. automated systems and specialized technicians oversee the alignment of the composite sheets to prevent any structural weaknesses. If a single layer is misaligned by even a small margin, the entire integrity of the rod is compromised when under load. One can notice how the rollers and mandrels move with rhythmic stability to maintain this level of precision. The process is only gaining momentum as the industry integrates even more advanced composite technologies into these everyday tools. Thus, the transformation of raw aerospace fibers into a finished sporting tool reaches a point of technical completion. This stage concludes the primary assembly, preparing the structure for its final refinement. Two primary materials form the foundation of the rod blank, consisting of carbon fiber pre-preg and fiberglass pre-preg. Why must these fibers be saturated with a heat-reactive resin before the manufacturing process even begins? The chemical composition of the resin is engineered to remain stable only under specific thermal conditions, hardening rapidly when subjected to intense heat during the final stages of production. But in reality, if the material remains exposed to standard ambient temperatures for an extended duration, the curing process initiates prematurely and renders the expensive fibers completely useless as waste. Because of this extreme thermal sensitivity, facility operators store all pre-preg rolls in specialized cold rooms maintained at temperatures strictly below 32 degrees Fahrenheit. The material is extracted from these frozen chambers only at the precise moment it is required on the factory floor. As soon as the technician removes the pre-preg from cold storage, a critical countdown begins to prevent chemical degradation. One can notice how the dark, tacky sheets are unrolled and positioned with absolute flatness across the expansive surface of the cutting table. The equipment gradually aligns with the technical outlines established by the engineering team during the design phase. It seems simple to lay out the fabric, but in reality, any wrinkle or misalignment will compromise the structural integrity of the final product. But this is just the beginning. A technician performs manual measurements to ensure the material edges align perfectly with the machine axes before the automated blade initiates its sequence. The mechanical cutter executes each pre-programmed pattern with a level of controlled precision that human hands cannot replicate. To maintain high productivity levels, the machine frequently processes between 8 and 10 layers of carbon fiber simultaneously in a single pass. Transition to the next level. Despite the thickness of the stacked material, the system must preserve dimensional accuracy down to small fractions of an inch. It is visible how the cutting head maneuvers across the table, as carbon is rarely sliced in traditional straight lines. Instead, the blades carve the sheets into intricate triangular forms and complex diagonal patterns. This specific cutting geometry is what dictates exactly how mechanical force travels along the entire length of the rod when it eventually bends under a heavy load. A single piece of fiber cut off by even a tiny fraction of an inch can shift the designated flex point of the rod entirely, ruining its performance characteristics. The process is only gaining momentum as these precisely shaped segments are collected for the next stage of assembly. The material remains cool and flexible, ready to be wrapped around the steel mandrels without delay. 150 tons of pressure are not required here, as the process begins with a far more delicate mechanical alignment. The material must be positioned with absolute precision onto the mandrel, a specialized stainless steel shaft that functions as the internal forming mold for the future rod blank. Why is the mandrel typically treated with a non-stick release agent? This preparation is essential because, after the application of intense heat, the finished blank must be separated from the steel core cleanly and without any structural damage. Once a layer of adhesive is spread evenly along the metal surface, a technician utilizes a small heated iron or a specialized localized heating tool to hot tack the initial layer of carbon fiber into its exact position. Each carbon piece is aligned with meticulous care along the mandrel's central axis, ensuring the edges are perfectly squared at both the tip and the butt ends before being secured. If this foundational layer is even slightly off-center, the entire rod blank will inherit that misalignment, compounding the error through every subsequent wrap. There are no automated robots or laser guidance systems involved in this critical phase. Everything depends entirely on the technician's trained eye and years of manual experience. But this is just the beginning. The process only gains momentum once the mandrel is placed onto the rolling table. It only looks obvious to watch the machine rotate, but it moves at a slow and strictly controlled speed while the carbon fiber is wrapped around the steel core. The entire operation remains under the craftsman's total command, ranging from the specific rotation velocity and hand pressure to the precise stopping points and the exact millisecond the next layer is introduced. As the core turns, one can notice how the fiber layers tighten against one another, closing the material edges until the rod gradually lengthens and tapers. The geometry follows a trajectory that has already been carefully calculated in the design phase. It seems simple to finish the main structure, but the technician must then add reinforcement layers at high stress zones, particularly near the handle area. These additional plies are not applied merely to increase thickness or raw strength. In reality, they are used to fine-tune the tactile feedback and the specific way the rod behaves during casting or while resisting the pull of a fish. Once the carbon fiber and reinforcement layers are fully wrapped, the blank transitions to the heat-resistant tape wrapping stage. The factory utilizes nylon tape, cellophane, or specialized vinyl to tightly bind the entire assembly before thermal processing begins. One can notice the mandrel being mounted onto a wrapping machine where the tape is applied in a continuous tight spiral. Each pass overlaps the previous one under consistent pressure from one end to the other. The purpose of this step is to lock the rod's geometry in place, keeping every carbon layer pressed firmly together throughout the upcoming heating cycle. As the tape tightens, the material beneath is compressed with total uniformity, creating a consistent wall thickness along the entire length of the blank. At this stage, the mandrel serves as the internal mold while the tape acts as the external mold. Everything only gets more complicated as the structure prepares for curing. 284 degrees Fahrenheit is the standard temperature the curing oven reaches for this transformation. The mandrels, now secured with heat-resistant tape, are hung onto specialized racks and moved into the heated chamber. The heating cycle is monitored by computer systems to ensure the temperature rises evenly and remains stable without any fluctuations. This phase usually lasts for approximately 2 hours, providing enough time for the heat-reactive resin to fully activate and complete its chemical change. Inside the oven, the resin begins to flow, spreading between the carbon fiber layers and bonding them into a unified, nearly monolithic structure. At first glance, the blank appears finished, but it is only during this thermal cycle that the separate layers merge permanently. Before curing, the blank can still be removed or adjusted if an error is detected. However, once the cycle is complete, any prior deviation is locked into the internal structure forever. Therefore, factories enforce extremely strict control over timing and oven stability during this critical window. When the heating ends and the cooling begins, the mandrel extraction stage commences. The blank is transferred to a dedicated separation machine designed for high-force operations. The metal mandrel is clamped firmly by a holding mechanism, while a pneumatic pulling arm applies a steady and powerful force to draw the core out of the rod. This pulling force must be strong enough to overcome the internal friction, yet remain smooth and precisely controlled to avoid deforming the cured carbon. If the heating process was executed correctly, the mandrel will slide out cleanly, leaving behind a completely hollow rod, blank. The technician then performs a quick inspection of straightness and uniformity, relying on tactile feedback and trained eyesight. The process is only gaining momentum as the outer wrapping tape is finally removed. One can notice the technician peeling the tape away in its original spiral direction, unwrapping it continuously from the tip to the butt. As the tape comes away, the blank is revealed with spiral marks and small ridges formed during the compression process. From here, the material is moved to the cutting station for final length shaping. The technician places the rod onto a support fixture and aligns it along the central axis before feeding it into the cutting blade. The blade rotates at a steady speed, removing excess material from both ends with high accuracy to bring the blank to its exact standard length. Dry sanding comes first in the finishing stage, breaking down the larger ridges and smoothing the marks left by the compression tape. The technician rotates the rod evenly by hand to ensure a uniform treatment around the entire circumference. After the initial pass, the blank is subjected to wet sanding. Water reduces the friction, carries away the resin dust, and allows for much finer control over the sanding pressure. After the surface is finished, the sections are moved to the joint fitting area. The technician inserts the tip section into the butt section to check the orientation and the physical integrity of the connection. 0.04 of an inch is the maximum deviation allowed at the joint before the continuity of force transfer is disrupted. the technician gently twists and shakes the assembly to feel for any looseness or play. A joint that meets the specification must engage evenly and remain silent when moved. Once the fit is approved, the sections are grouped into bundles by model and length. These bundles are secured neatly and sent to the painting workshop. The blank is then mounted onto a rotating machine that applies paint evenly around the entire circumference. The first layer is typically a white base primer used to unify the surface and enhance the vibrancy of the subsequent colors. Once the base coat has dried, the blank receives its primary color coating. High visibility paints are commonly used at this stage to improve visibility during outdoor use in low light conditions. Depending on the specific order, the rod may also be customized to meet individual requirements. The process concludes with a clear urethane top coat, which is sprayed or wiped on to create a smooth finish that resists scratches and ultraviolet exposure. The material is then placed into a drying room to stabilize before being transferred to the handle assembly area. Here, all handle components are installed entirely by hand. The technician applies adhesive along the blank and slides each section, whether it is made of cork, EVA foam, or heat shrink tubing, into its designated position. Next comes the installation of the reel seat, which must be aligned perfectly along the rod's central axis. Even a slight misalignment here would create discomfort for the user and alter the feel of the rod under a heavy load. One can notice how the blank begins to take on the character of a finished tool as the butt cap or gimbal is fixed in place. After the handle is installed, the guide installation stage begins. The technician marks each guide position along the length of the rod to determine how the fishing line will travel and how the load will be distributed. Each guide is placed onto its mark and aligned by eye along the central axis. Once the position is correct, the technician begins wrapping thread around the guide foot with high tension. One hand holds the guide steady, while the other ensures every wrap sits cleanly beside the next. After all guides are wrapped, the rod moves into the epoxy coating stage. The technician uses a brush to apply a base layer of epoxy over each thread wrap, ensuring the resin penetrates fully to bond with the blank. Once the base coat is applied, the rod is placed onto a rotating rack or a turning drum. This rotation allows the epoxy to level itself perfectly around each guide under the influence of gravity. Next, the rods are passed through a hot airflow or an ultraviolet curing chamber to stabilize the wraps before a final glossy coat is brushed on. In a single day, the factory consumes a vast volume of finishing material to process dozens of rods at once on the rotating racks. After the assembly is complete, the tip and butt sections are joined together for the final time. The connection must engage evenly and slide smoothly throughout the entire insertion range. The rod is then placed on an inspection table where the technician rotates it slowly to confirm axial straightness with the naked eye. Finally, the rod is flex tested under a controlled load to verify its structural stability and balance. The material is ready to move to the next processing phase without haste. 100% of the sensations an angler experiences when holding a finished fishing rod are defined by the consistency of its mechanical responses. Why is this uniformity so critical for the person on the water? It only looks obvious that a rod should bend and vibrate. But in reality, every subtle oscillation transmitted through the grip is the result of hundreds of technical decisions shaped within the factory walls. This reliability determines whether a tool can be trusted during the physical stress of real-world use. The process is only gaining momentum. One can notice how the structural integrity of the rod remains constant across thousands of identical units. It is visible how the materials react to tension with predictable precision, ensuring that no sudden failures occur under load. Such a result is achieved because manufacturing standards allow no deviation in the density or alignment of the internal fibers. The equipment gradually verifies the resonance of the blank to ensure every vibration follows a calculated path to the handle. It seems simple at first glance, but this level of technical uniformity is what transforms a composite tube into a precision instrument. The material is ready to move to the next processing phase without haste. Thus ends one of the key stages of ensuring quality in the production of professional tools.